Okay, so picking up where we left off yesterday, we were talking about the fundamental theorem of calculus, and we were exploring definite integrals. Okay, it's important to know this, that differentiation, so finding the derivative, and integration are inverse processes. Okay? One undoes the other. And we talked about that when we started differentiation and then moved into, when we started anti-differentiation. Okay, an antiderivative undoes a derivative. These were the questions we were working on when we finished yesterday's video. So let's just kind of work through this. Now remember, to do the definite integral, I know it's a definite integral because it has an upper and a lower bound. What we do is we find the antiderivative of sine x, which would be negative cos x. We choose the antiderivative where c is 0, so I don't need to write plus c or plus 0. I'll just leave it as negative cos x. And I'm going to evaluate that from pi to 2 pi. So what I do, get my black pen, is I am going to sub my upper bound, my 2 pi in, and then I am going to sub my lower bound in, 1 pi. And it would probably make most sense to distribute the negative now and call this plus. Okay, that would become a positive cos x. So b value goes in, a value goes in, and away we go. I'll work this out. Now keep in mind this would be like, in order to determine this, it would help if we remembered our unit circle. Okay, pi is over here, 2 pi is over here. This is the point 1 comma 0. This is the point negative 1 comma 0. So the cosine of 2 pi, that's the x coordinate. This would be a negative. This here would be a 1. So times this negative 1 would give me a negative 1. Plus the cosine of pi, that's this. All right. So I'm adding a negative 1 to that. It gives me an area of negative 2. Notice I said an area because a definite integral, as we saw yesterday, is a way to calculate the area under a curve. So if I looked at the curve from of sine x between pi and 2 pi, so between here and here, there's the x-axis. The area of this shaded region right here would be negative 2. Okay, there's my 0, pi over 2, 1 pi, 3 pi over 2, and 2 pi. So I was going between pi and 2 pi. And I was calculating the area between the x-axis and the curve. Notice it's a negative area because that area lies below the x-axis. If I was going between 0 and pi, I think we could agree that this area would be positive 2. Okay, so that's a little visual representation of what we're calculating. Next one, all right, I want to do the antiderivative of 1 over 1 plus x squared. This looks kind of complicated, but that is one of the general antiderivatives from your table that you are supposed to know. The antiderivative of 1 over 1 plus x squared is actually inverse tan, or arctan, x. Don't need to write plus c, remember? Okay, antiderivative where c is 0, and I'm going from 0 to 1. So to calculate this, I'm going to do the inverse tan of 1 and subtract the inverse tan of 0. So the 1 goes in first, the 0 goes in second, and we solve. Now keep in mind what this is asking you. It's asking you what angle has a tangent value of 1. Well, the answer to that would be pi over 4. And this is asking you what angle has a tangent value of 0, the y divided by the x. That would be a 0. So I end up with pi over 4 minus 0 gives me pi over 4. All right, and it might help if you remember this triangle in pre-cal A. This side is 1, this side is 1, the hypotenuse is root 2. So the tangent of pi over 4 is 1 over 1. Okay, it's not a very nice looking pi over 4, but that's what it says. Okay, so there's 2 more examples. You can try these guys, all right? Maybe you can pause the video. You can try those 4 on your own, okay? And then unpause the video and I'll go through them, see how you made out. So good luck. So we're calculating the area under the curve x squared plus 2 from 2 to 4. And when I do this, I'm going to get the antiderivative to be x cubed over 3 plus 2x. Okay, the antiderivative of x cubed would be x cubed, sorry, the antiderivative of x squared would be x cubed over 3. The antiderivative of 2 would be 2x. And I'm going from 2 to 4. So I'll fill a 2 in first, 4 in first. Then I'll fill a 2 in. And then I'll subtract. So the 4 goes here. Remember, it's capital F at B minus capital F at A. And B is 4 and A is 2. So here's what I get. 4 cubed, that is 64 over 3. 2 times 4, that's 8. Okay, this would be 8/3. 2 cubed is 8 over 3, so I'm going to distribute the negative to give me negative 8/3. And I'll distribute the negative over this. 2 times 2 is 4, times the negative 1 would give me negative 4. I'll group these together. 64 minus 8. Okay, they'll put these guys together first because they have a denominator of 3. 64 minus 8. That will give me 56 over 3 plus, okay, 8 minus 4. That's going to give me 4. So 64 over 3 minus 8 over 3 gave me this. 8 minus 4, grouping those, gave me this. Add those together, 56 over 3 plus 12 over 3, 4 over 1 would be 12 over 3, is going to give me a total of 68 over 3. That's what the area would be, 68 over 3. All right. I believe we did this one, or we talked about this one just a second ago. Okay, the answer to this should be from 0 to 2. Oh no, it's from 0 to 2 pi. My bad. Okay, 0 to pi over 2. So it's not the same. I was saying from 0 to 2 pi. So this should actually work out to be 1, but we'll check it out. So the antiderivative is going to equal, so the antiderivative of sine x is negative cos x. And I'm going from 0 to pi over 2. So I will find the negative, or the cosine of pi over 2, and I'll multiply it by a negative 1. And then rather than subtract, rather than saying this, negative, negative cos, I'll just make that a positive. Okay, so it'll become plus the cosine of 0. Again, if I talk about my unit circle, here's pi over 2, that's the point 0, 1. Here's 0 radians. Okay, that would be here, that's 1, 0. So I end up with the negative cosine of pi over 2. Well, the cosine of pi over 2, this would work out to be a 0 times negative 1. Well, that's just going to be 0. And the cosine of 0, that's this x-coordinate, that works out to be a 1. So I end up with 0 plus 1 gives me 1. Okay, now let's look back to here. Remember I said from 0 to pi, that should give me an area of 2. Well, if I just go from 0 to pi over 2, it's going to give me half that area, which would be 1. And that's what the math proves right here. Next one, All right, the antiderivative of e to the x is e to the x, and I'm going from 1 to 3. So this is going to equal e to the third minus e to the first. So I filled a 3 in first, then I filled a 1 in second, and now I'm subtracting. And that's your answer, or think about what you might do to this. Your answer would probably show up in its factored form. Both terms have an e in them. So if I factor out an e to the first, that would leave e squared, excuse me, minus 1. E times e squared minus 1. So I've got 1 and 68 over 3. Finally, the last one. Okay, here's a common mistake with this one. It says, be careful, what about this one? Why is it different? Does the fundamental theorem of calculus apply? Most people would jump into this one and write it as, so they'd rewrite the integral from -1 to 3 of x to the -2, integrating with respect to x. They would do the antiderivative, x to the -2, so you're going to add 1 to the -2, would give you x to the -1, and you'll divide by the new exponent, -1, and we're going from -1 to 3. And when I solve this, you could write that as -1 over x, which would equal, go up here, -1 over 3 minus -1 over, and this would be -1. So I'd fill the 3 in here, capital F at b, or the antiderivative at my b value, minus capital F at a, fill my -1 in here. So this is going to equal -1/3 minus -1 divided by -1, that's a +1, so I'd have -1. So I get -1/3 minus 3/3, which would give me -4/3. So you might say, what's wrong with that? Well, the reason it can't equal -4/3, that's what this should show, can't equal -4/3, is because of this rule right here. When we explored the fundamental theorem of calculus, we said that the function, or f, has to be continuous on a to b. All right? When I look at this function right here, would that be continuous from -1 to 3? First of all, where is 1 over x squared discontinuous? If you said it's discontinuous at x equals 0, you are correct. And 0 is between a and b. It's between -1 and 3. So since it is discontinuous between a and b, we can say that the fundamental theorem of calculus does not apply, and it has no area. Okay? There'd be a vertical asymptote at x equals 0, or an infinite discontinuity is what they'd call it. Infinite discontinuity, or a vertical asymptote. And we talked about those in our Pre-Calculus B course. Only applies to continuous functions. Since there is an infinite discontinuity at x equals 0, it is not continuous on the interval from -1 to 3, then the integral does not exist. Okay, so there would be no area for that. So those are 4 more examples of definite integrals. Remember, if it was just, say I just wanted the indefinite integral of this, so this is a definite integral because it's got an upper and a lower bound. If it were indefinite, it would look like this. And my answer would just be x cubed over 3 plus 2x plus c. That's where I would stop. I would not have to evaluate capital F at b and then subtract capital F at a like I do with the definite integral, and I would get this particular number. Remember, that number represents the area under the curve. This represents all functions whose derivative is equal to x squared plus 2. Okay, and you could prove that's true. Like I said, they are inverse operations. If you took the derivative of 1/3 x cubed, you'd get 1/3 times 3 would give you 1 x squared. The the derivative of 2x would be 2, and the derivative of the constant would be 0. It would bring me back there. So indefinite integrals, you need to write the plus c. Definite integrals, we use the antiderivative where c is 0, and we evaluate capital F at b, and we evaluate capital F at a, and we subtract the 2. These are the questions that you can work on from the textbook.